Hi everyone, I am Maiko Kuan and I am from BSME-1B. In this video, we will be learning and understanding about the 5 topics in our differential calculus subject. Namely, they are the rate of change, the basic rules of derivative, the chain rule, the derivative of inverse trigonometric function, and the derivative of hyperbolic and inverse hyperbolic function. And there's only one learning objective in this video, and it is for you to learn about these topics. So, let's start. So, the first topic that we will be discussing today is the rate of change. The expressions such as meter per second, miles per gallon, miles per hour, gallon per minute, and the likes, they all represent rates. The ratio delta y over delta x is called the average rate of change over the interval. If we let delta x approaches 0, the ratio in general approaches a limiting value which defined as the rate of change of y corresponding to the given value of x, or in instantaneous rate it would be like this. So dy over dx equals the limit of delta y over delta x as delta x approaches 0, and it is called the rate of change of y with respect to x. Also, when we are talking about the rate of change, we will simply be following 3 main steps. And the first step is to identify the formula of a certain problem. For example, when we talk about, or when the problem talks about the volume of a circular cylinder, then your first step would be V is equal to the quantity of pi r squared times height. And next, the find the derivative of the formula using delta method. And the last step will be find the rate of change from the derivative where the denominator approaches 0. Like what I said earlier, dy over dx is equal to the limit of delta y over delta x as delta x approaches 0. So for you to fully understand or understand more about the rate of change, I will be presenting to you an example for it. So here are the examples of the rate of change. We have the area of a circle, volume of a sphere, and the volume of a cube. So let's start with the area of a circle. The area of a circle is A is equal to pi r squared. So first you have to, since we already identified the formula of a certain problem, which is the first step of the rate of change, we will be proceeding to the next step of the rate of change, which is to find the derivative of the formula using delta method. So A plus delta A is equal to pi times r plus delta r squared. Delta A is equal to pi times substitute or simplify r plus delta r squared using FOIL method or the Pascal's triangle. So it would become r squared plus 2r delta r plus delta r squared minus a, and our a here will be the area of the circle, which is the pi r squared. So let's simplify this. So delta a is equal to multiply the pi to the inside of the parenthesis, so it would become pi r squared plus 2 pi r delta r plus pi delta r squared minus our a here will be the area of the circle, as I've said already, which is the pi r squared. So we'll put here the pi r squared. Next is to divide both sides by delta r. So delta a is equal to, but first you have to exclude or put outside the parentheses the delta r. So it would become delta r times 2 pi r plus pi delta r. I'll divide both sides by delta r, and as you can see, delta r squared here and here will be cancelled out. So delta A over delta R is equal to 2 pi r plus pi delta r. And next, the third step is to find the rate of change from the derivative where the denominator approaches 0. So we have here limit of our denominator here is delta r approaches 0. So 2 pi r plus limit as delta r approaches 0 pi delta r. So we don't have delta r here, so it will be remain. And here we have delta r here, so pi times delta r, which is 0, is equal to 0. So our delta r over delta a rather over delta r will be 2 pi r, and this is our rate of change from the area of a circle. And our next example of the rate of change will be the volume of a sphere. So we already also identify the formula of a certain problem, and so we will be proceeding to the second step, which is to find the derivative of the formula using delta method. So we'll be using the delta method from the volume of a sphere. So it would become S plus delta S is equal to 4 over 3 pi times R plus delta R cube. So you could use the Pascal's triangle to this to simplify this parentheses. So it would become delta S is equal to 4 over 3 pi. Pascal's triangle of R plus delta R cube will be R cube plus 3 R squared delta R plus 3R delta R squared plus delta R cube minus S. And our S here again is the volume of a sphere, which is 4 over 3 pi R cube. So delta S is equal to 4 over 3 pi. So let's first substitute the 4 over 3 pi to the parentheses. So it will become 4 over 3 pi R cube plus 4 over 3 times 3 will become 4 pi r squared delta r plus 4 pi r delta r squared plus 4 over 3 pi delta r cube minus the S, which is 4 over 3 pi r squared. So 4 over 3 pi r cube. So let's cancel the same terms or the unlike terms. So we'll be canceling 4 over 3 pi r squared, the positive and the negative. So we will be left with delta S is equal to, we have to exclude again or put outside the parentheses again the delta R. So delta R times 4 pi r squared plus 4 pi r delta r plus 4 over 3 pi delta r, and divide both sides by delta r, cancel delta r. So we'll have delta S over delta r is equal to 4 delta r squared plus 4 pi r delta r plus 4 over 3 pi delta r. So next we will be proceeding to the third step of the rate of change, which is to find the rate of change from the derivative where the denominator approaches 0. So again, our delta r will be approaching 0. So it would be the limit as delta r approaches 0 of 4 pi r squared plus the limit as delta r approaches 0 of 4 pi r delta r plus the limit of delta r approaches 0 of 4 over 3 pi delta r. So we have delta r here, so this should become 0, and we also have delta r here, and if it will be multiplied by 0, it will become 0. So we will be left with 4 pi r squared. So that would be the rate of change of the volume of sphere. So delta S over delta R is equal to 4 pi r squared, and that is our final answer. So our last example of the rate of change will be the volume of a cube. So the volume of a cube is a cube. So we already identified the formula of a certain problem, and so we'll be proceeding to the second step in finding the rate of change, which is to find the derivative of the formula using delta method. So v plus delta v is equal to a plus delta a cubed, and also as we have done to the previous example, we'll also be using the Pascal's triangle in order to simplify the parentheses. So delta v is equal to the Pascal's triangle of a plus delta a cube will be a cube plus 3a squared delta a plus 3a delta a squared plus delta a cubed minus v, and our v here is a cube. So let's substitute it first, a cube. So we can cancel negative a cube from the positive a cube, so we'll be left with delta v is equal to 3a squared delta a plus 3a delta a squared plus delta a cube. And we also have to separate the delta a outside the parentheses. So delta v is equal to delta a times 3a squared plus 3a delta a plus delta a squared. So divide both sides by delta a, cancel delta a. So we'll be left with delta v over delta a is equal to 3a squared plus 3a delta a plus delta a squared. So we'll be following the third step, the last step of the rate of change, which is to find the rate of change from the derivative where the denominator approaches 0. So delta a here, our denominator will be approaching 0. So limit of delta a approaches 0 of 3a squared plus limit of delta a approaches 0, 3a delta a plus limit of delta a approaches 0 of delta a squared. So we have delta a here, so it will be automatically 0, and also here it will be automatically 0. And our first term, 3a squared, doesn't have delta a in it, so we'll be remaining, or we'll be copying the first term. So the delta v over delta a, which is the volume of a cube, will be 3a squared. And this is our final answer. This is the rate of change of the volume of a cube. So the next topic that we will be discussing now is the basic rules of derivative. So the derivative of a function y is equal to f of x of a variable x is a measure of the rate at which the value of y of the function changes with respect to the change of variable x. It is called the derivative of f with respect to x. Differentiation is the process of finding a derivative, and the derivative of the function is the rate of change of the output, or the rate of change of the output value with respect to its input value, where differential is the actual change of function. So when we are talking about the basic rules of derivative, we will also be talking about the 5 basic rules of derivative, and they are here. So the first basic rule of derivative is that the derivative of c constant is equal to 0. Let's take, for example, y is equal to c, or any number 1, 2, 3, 4, 5, 6, 7, and the derivative of it is or will be equal to 0. And the number 2 basic rule of derivative is that the derivative of the sum of two functions is equal to the sum of their derivative. So let's take, for example, y is equal to u plus v. So it would become dy over dx is equal to du over dx plus dv over dx. And the number 3 basic rules of derivative is that the derivative of the product of two functions is equal to the first function times the derivative of the second function times the derivative of the first function. So here is an example. So y is equal to uv. So it would become du over dx or dy over dx is equal to u dv over dx plus v times the derivative of u over dx. And the fourth basic rule of derivative is that the derivative of the quotient of two functions is equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. So here is an example or the illustration. So y is equal to u over v, and it would become dy over dx is equal to v times du over dx minus u times dv over dx all over v squared. And the last basic rule of derivative is that the derivative of y is equal to xn. So if n is equal to y, then it would become dy over dx is equal to nxn minus 1, and the derivative of the x over n, which n is equal to 1, is 1. So just like the rate of change, for you to fully understand or deeply understand the topic, I will present to you an example of the basic rule of derivative. So you already know the 5 basic rules of derivative, and now we will be or I will be presenting to you an example for you to hopefully fully understand or understand deeply the basic rules of derivative. So let's start. F of y is equal to y to the power of 5 minus 5y to the power of cube plus 2y all over y cube. So you'll be simply dividing the numerator from the denominator. So y5 divided by y cube is y would be y squared minus 5y cube divided by y cube. Simply cancel the y cube, and the remaining will be 5 plus 2y divided by y cube will be 2y to the power of negative 2, and you will be finding the derivative of the individual terms. So what is the derivative of y squared? So it would be 2y minus the derivative of 5, which is constant, so it would become 0, plus the derivative of 2y negative 2. So 2 times negative 2 is negative 4 times y negative 2 minus 1 is negative 3. So f of y is 2y minus 4y negative 3, and this would be our final answer. And another example is that n is equal to x times 5x cubed minus 15. So you'll be putting or multiplying the x from the inside of the parentheses. So x times 5x cubed is 5x to the power of 4 minus 15 times x is 15x. So same process, you'll be finding the derivative of the individual terms. So the derivative of 5x4 is 5 times 4 times x to the power of 4 minus 1 minus the derivative of 15x is 15. So it would be 5 times 4 is 20, x 4 minus 1 is 3 minus 15. So this would be our final answer as well. So the third topic that we will be discussing now is the chain rule and general power rule. So let's note that u is a binomial or multinomial function of x, and n is power of exponent. So there is the example. Y is equal to u to the power of n. So y prime or dy over dx is equal to n u power of n minus 1 times the derivative. It's just like the fifth basic rule of derivative. So for you to understand what the chain rule is, here is its example. And now, this is the example of the chain rule. So y is equal to cube root of 1 minus 8z. So first we'll be transforming the equation into its another form. So it would become y is equal to parentheses minus 1 minus 8z to the power of 1/3. So we'll be applying the chain rule here. So bring down the exponent 1/3 times the quantity of the parentheses, which is 1 minus 8z. So 1/3 minus 1, and then the derivative of what's inside the parentheses, which is 1 minus 8z. So 1 over 3 times 1 minus 8z, 1/3 minus 1 would become negative 2 over 3 times the derivative of 1, which is constant, so it will be 0, and the derivative of 8z is 8. So simply multiply the both constant here, which is the 1/3 and 8, so it would become 8, or this is negative 8. By the way, the derivative of 1 minus 8z is negative 8. So negative 8 times 1/3 will become negative 8 over 3 times the quantity of 1 minus 8z to the power of negative 2 over 3. And this would be our final answer. And another example for this is some sort of substitution only. So let's take, for example, RW is equal to cosecant 7W. So the derivative of cosecant is cosecant times cotangent. So you'll be simply substituting the derivative of cosecant to its respective derivative. So it will become negative 7 cosecant the 7W times cotangent 7W, and simply this would be our final answer. The second to the last topic that we will be discussing in this video is the derivative of inverse trigonometric function. So let u is a function of x or independent variable. So you will see here the conversion or the derivatives of a certain given, the arcsine, arccosine, arctangent, arccotangent, arcsecant, and arccosecant. And now let's apply some of these formulas into an example for you to understand it more. So example of the derivative of inverse trigo. Y is equal to 5x6. We can use the chain rule here, minus the arcsecant x. So here we can see the second to the power of negative 1, or arcsecant. As we read this, x will be simply transforming it into its constant and respective derivative. So we'll be starting to chain rule this equation here. So according to what we have learned, the chain rule, so we'll be bring downing the exponent 5, so times 6x 6 minus 1 minus the derivative of arcsecant will be 1 over the variable, which is the x, square root of x squared minus 1 times the derivative of what's inside the parentheses here, and we have x here, and the derivative of x is, so we already know that this is 1, so you have to simplify this already. So 5 times 6 is 30, x 6 minus 1 is 5, minus 1 divided by x square root of x squared minus 1, and the derivative here is 1, so there's no need to put 1 here. So this would be our final answer. And another example for the derivative of inverse trigonometric function is that here gt is equal to cosecant to the power of negative 1t, or the arccosecant, minus 4 cotangent to the power of negative 1 times t, or the arccotangent. So same process here. you'll be transforming the r cosecant to its corresponding and respective derivative. So it will be negative 1 over t to the power of t squared minus 1. And here we'll be transforming the cotangent or r cotangent to its corresponding derivative with the 4 in it. So it will be negative 4, copy here, minus negative 4 over t squared plus 1. It supposedly it is 1 here, but we have negative 4 here, so 1 times negative 4 is negative 4. That's why we arrive to the negative 4 here. So next is just to simplify this equation. So gt is equal to negative 1 over t times the square root, or the square root of t squared minus 1, 1 times negative 4 plus 4 t squared plus 1, and this would be our final answer here. So those are the examples of the derivative of inverse trigonometric function. So our last topic in this video is the derivative of hyperbolic and inverse hyperbolic function. So just like the derivative of inverse trigonometric functions, we also have constant derivatives of the hyperbolic and inverse hyperbolic functions. As you can see here, these are the constant derivatives of the hyperbolic function. So derivative of sine hx up to the derivative of the cosecant hx. And also, we have the constant derivatives of the inverse trigonometric function. So we have here sine h negative 1x up to the tan h negative 1x. And for you to understand more this topic, we'll be having an example for both the derivative of hyperbolic and the derivative of inverse hyperbolic function. So derivative of hyperbolic function, we have here rt is equal to tan t plus t squared cosecant h times t. So just like the derivative of inverse trigonometric function, the derivative of hyperbolic function also follows some certain rule or constant corresponding derivative of like tan and cosecant h. So to transform or to find the derivative of tan t, it would be secant squared times t plus t squared, the derivative of cosecant ht plus cosecant ht, then the derivative of t squared. So as you can see here, t squared times cosecant h, let t squared be the u and the cosecant h be the v. So we'll be using the basic rule, or the basic rule of derivative, third derivative, which is the derivative of product. So it would be u dv plus v du. So next is to simplify it. So it would become secant squared t plus t squared minus cosecant ht. The derivative of cosecant ht is negative cosecant ht times cotangent ht plus cosecant ht times the derivative of t squared, which is 2t. So next is to arrange the terms. So it would become secant squared t plus 2t cosecant ht minus t squared cosecant ht times cotangent ht, and this here would become our final answer. Now we have here the example of the inverse hyperbolic function. If a while ago we discussed about the derivative of hyperbolic function, now I will be giving you an example about the derivative of inverse hyperbolic function. So f of x is equal to x to the power of f cosecant h negative 1 or r cosecant h times f squared. So you'll be using the third basic rule of the derivative again, which is the product rule. So let x of f be the u and cosecant h to the power of negative 1 f squared be the v. So it would become f of x is equal to v x of f the v du, and our u here is cosecant h to the power of negative 1 f squared plus cosecant h negative 1 f squared, then the derivative of x to the power of f. So f of x is equal to xf, and the derivative of cosecant h negative 1 f squared would be negative 1 divided by f to the square times the square root of 1 plus f squared, and then the derivative of f squared, and then plus the cosecant h negative 1 f squared. The derivative of xf would still be x to the power of f. Next is to substitute the x to the power of f to the negative 1, or to simplify this given here. So it would become negative x to the power of f divided by f times the square root of 1 plus f squared. The derivative of 2f is the derivative of f squared here, it would be 2f plus cosecant h to the power of negative 1 f squared, copy xf. Next is to simplify it all and arrange the terms. So you will be simplifying negative x to the power of x to the 2f, the negative x to the power of f to the 2f. So it would become negative 2f xf over f times square root of 1 plus f squared plus xf. You arrange this, so it will become xf times cosecant h negative 1 f squared. And this is our final answer. This is our example of the derivative of inverse trigonometric or inverse hyperbolic function rather. And that sums up my discussion in this video. And to recap, I discussed the rate of change, the basic rules of derivative, the chain rule, the derivative of inverse trigonometric function, and the derivative of hyperbolic and inverse hyperbolic function. I hope you learned something. I am Maiko Kuan, and I thank you for watching.